Okay, so today's lesson is objective 2.1D. 2.1D. And our topic for today is factoring special cases. Our instructional objective for today, you will be able to recognize perfect square trinomials and the difference of perfect squares. And also you'll be able to factor them, quickly and accurately. So I'll give you a moment to write that down. So again, our objective, big objective, huge. The first part of that objective, it's huge. Recognize perfect square trinomials. You look at them and you recognize them as perfect square trinomials. And also recognize the difference of perfect squares. They're a little easier to recognize than perfect square trinomials. So you'll probably have a little easier time with those. And then of course, what we're going to use is a formulaic plan to solve them or factor them quickly. Okay, so are you ready? Okay, so we're going to go back and forth between the boxes on the left and right. We're going to start with our notes for the perfect square trinomials. And we're going to start right here at the top. And in the back, can you see that? Or would you like me to zoom in a little bit? You guys are good? Speak up. Okay. So what I'm going to ask you to do is I'm going to ask you to multiply a plus b quantity squared. When you look at this, would you agree that this is a perfect square? No. Of course it is. Look at it. It's a perfect square. So when and it's a binomial factor, a plus b times a plus b. So if we multiply that out, something is going to occur. Okay, so we would just use our distributive skills to multiply. A times a is a squared, right? Right? And then a times b is ab. And then we're going to come back and I'm going to do this one. B times a is also ab. Notice that there are two of them. And then, of course, we'll do our last multiplication here, which would be a positive b squared. So now, of course, we simplify that, but the big deal here is that there are two ab's in the middle. So we'll write it as a squared plus 2ab's plus b squared. The 2ab is really important when you're recognizing that this is a perfect square trinomial. So the rule says this. Notice what this says. It says the same exact thing that this says. So if I'm asked to factor this, then I can quickly recognize that this is a perfect square. And this is a perfect square on each end. And the other thing that's going to make this possible is that here it's positive. So that means we either have a negative times a negative or we have a positive times a positive, but your last term is positive and your first term is positive. And what you have here in the middle, this is the big deal, the thing in the middle. It's 2 of each part of your perfect square, 2ab. There's 2 of them, 2 a's, 2 b's, 2 of them. That's the important part. Okay, so the answer to this is factored very quickly, this a plus and we use this symbol right here to help us determine that it's going to be positive. B, close quantity squared. Now, of course, I could prove this with the AC method, and I'm going to, but please don't write it down. Just watch so that you can connect it to what we already know. If I use AC method, what's my A times C? 1, right? Because it's 1 times 1. And what's my B? So what are the two factors? 1 and 1. Okay? So if I were to bust this up, it would factor down to this. It would. Okay? So we know a lot of times that we're dealing with a perfect square trinomial when we try our AC method and the numbers that we find that we're looking for are the same. Okay, then we know that we probably could have done this with a lot less work. All right, so I'm not going to go on to the next problem in that box. I'm going to go ahead and scoot over. That's not scooting over. How about we scoot over? Thank you. To these problems here. And what we're going to do is we are going to factor this problem here together. So first, let's recognize that this is a perfect square trinomial. By understanding this is a perfect square, do you agree? And this is a perfect square. And so if I can get this middle term to be 2 5s and 2 2s, what's 5 times 2? And 10 times 2 is 20. Did you see it? What's 5 times 2? 10, and 2 10s in the middle, 20. So I could say that this is 5x and 2y, just taking their square roots, and I'm going to use this sign, quantity squared. So it factors very quickly. I always will do just a little check, and of course you don't need to write this, but if you don't mind, I'm going to do a little check, and then I'm going to show you how I shortcut this check, multiplying 25x squared, yes, 10xy plus 10xy is 20xy, and 2y times 2y is 4y squared. So you can see that the check works. All right, so you do the next one. Okay. So did you get that? 7a plus 3 quantity squared is what you should have got. Let's double check it. 7a squared. What is this squared? 49a squared. Okay. What's this squared? Okay. Now let's multiply this together. What's 7a times 3? 21. Do it again. 21a plus 21a is 42a. So that's how I check it. Instead of writing it out twice, I just square the first number, square the last number, and then I do 2 multiplications of those numbers to get the middle number. All right, so there we have 2 examples of the sum of, a perfect square trinomial where all of our numbers are positive. Now we're going to go down to the next example that asks you about when your b is negative. Excuse me. So let's multiply that out. Now I already showed you a shortcut, right? Square it. Square it. What's a squared? What's a times a? A squared. All right. Multiply this times that. Watch. Isn't that a negative AB? Okay, negative AB, do it again. Negative AB, so it's negative 2ABs. Now square the last one. Negative B times negative B is positive b squared. So there you can see that this is a perfect square, and it turns into what we call a perfect square trinomial. So therefore, this little dot, 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 if you didn't know, is a math symbol that says therefore, or as a result, or in connection to. It's a nice little way to write it. Hey, what's up, Gloria?
I have a pass for Iris.
Iris. Okay, Iris, you have a pass here. If you want to wait till we're finished with this, it's to guidance. Where are you? You're over there. You can go if you need to. Okay, I was looking in the wrong spot. That's because Iris in first period sits right there. I'm just not thinking. Okay, so what's the rule? It says if our first number is a perfect square and our last number is a perfect square and our middle term is a negative 2 of times AB's, we can say that the answer is negative A minus B quantity squared. They're just reverses of each other. This is multiplication, and this is division. It's factoring out. Okay? All right, there is a typo on our notes over here. I keep doing that. I want to grab the page, and I forget to use my select button. I would like to do this problem, but we do have an error. Would like to change this from a 1 to a y squared. So if you would, please do that. We're going to do this one together. Okay, here we go. Is the first number a perfect square? Is the last number a perfect square? Okay, so what's the square root of 64x squared? 8x. And how about the square root of y squared? Y. All right. Should I use a positive or a negative? Because this is positive, but this is so minus. Okay, now let's check it before we write a square on it. So we got 64x squared if we square that, right? Multiply that times that. Negative 8xy. Do it again. So negative 16xy. And then square. Y squared. So, yep, it's a perfect square trinomial. Okay? All right. You do the next one. Check your answer against mine when you're done. God bless you. Are you good? Are you ready? Need more time? I have 7a minus 5 quantity squared. With a quick check, square it, 49a, multiply it again, add them together, negative 70a, square it, 25. So it's good. All right, so we're going to move on to this last problem. I did it again. Here we go. All right. Excuse me. Sorry, those of you that are listening to this on video. Okay. Does this fit the criteria for a perfect square trinomial? Is the first number a perfect square? 6, right? And the last number is a perfect square? 9. And 6 times 9 is 54. And 54 plus 54 is 108. So yes, this is a perfect square. However, there is a GCF. What is it? It is 9. So let us factor out a 9. So we get 9 times 4a squared minus 12a plus 9. And then we ask ourselves, is it still a perfect square trinomial? Is this a perfect square? Is this a perfect square? And this would be 2 and 3. And 2 times 3 is 6. 6 times 2 is 12. Yeah, I think so. So I think we could say that the answer is 9 times 2a. Shall I use minus or plus? You betcha. And it's factored. Now, I know that you're going to get in a groove and you're not going to always see the GCF. So let's say that you instead, I'm going to write this, or you factored that out to, would you agree, 6a minus 9 quantity squared, 36, yes? 54 and 54, 108, 81, absolutely. But don't you see a common factor in 6 and 9? 3. So you know what you've got to do? You have to actually bust it up into two terms and factor the 3 out of each pair. So 3 times 2a minus 3, and again 3 times 3 times 2a minus 3, and then of course rearrange 9 times 2a minus 3 quantity squared. So certainly a lot clumsier, a lot more places that you can go wrong. You should always check your final answer to make sure it's fully factored and there's no common factors left. Okay? So we now will end with the difference of perfect squares, which in my opinion happen to be, the most simple of all the factorings. So you'll notice it's not a trinomial anymore. It's a binomial. It's the difference, meaning we're subtracting, the difference of perfect squares. So let's multiply, because multiplication is the opposite of factoring. Factoring is division. Multiply. A times A squared. A times B, AB. Come back. Negative B times A, negative AB. And then negative B times positive B, negative B squared. And what happens to these center terms? They cancel each other out, which leaves you with A squared minus B squared. And the first number's a square, and the last number's a square, and you're subtracting them. So whenever I'm in this situation, therefore, where I have an A squared minus a B squared, we call this a difference of squares. So we would factor it out using the squares with one addition and one subtraction. And of course, it doesn't matter if you do A plus B, A minus B. That doesn't matter as long as you have one of each type of B. Okay? And so this is how you would work on perfect squares. It's a binomial, and it's got to be subtraction. Why do we need the subtraction in order for this to factor quickly? We'll say it again. Why? What was the thing that caused this, which usually turns into a trinomial, into this? What was the thing that happened? The outside inside terms canceled out. And they were exactly the same. Actually, they were exact opposites. One was positive AB and one was negative AB. So we need this to be negative in order to get a negative B and a positive B. All right. So we're going to go to the other side quickly. You're probably already done with it. And here you notice that this starts with the constant. It's not written in descending order, right? Usually we see the x squared first, but it's rearranged because I don't want to lead with a negative. Here's what I don't want to see. Negative x squared plus 9. I don't want to have to factor that to negative x plus 3 and x plus 3. I don't want to do that. I can, but it's not really, it's clumsy. It's a little messy. We always like to lead with a positive. So we're going to factor it out. So we're going to take our 9 and split it into 3 and 3. And we're going to take our x squared and split it into x and x. One negative, one positive. Got it? Okay, you do one. So you should have split it into 2 A's and 11 B's. 1 positive and 1 negative 11B. And can I go any further? Do we have common factors? Nope. Okay, so there we have that. So we're going to go ahead and do one more, and then we're going to go back and talk about the sum of perfect squares. So here we go. What do you see? I see a binomial. I see some perfect squares, but I see some other things. A GCF. What is it? 9 and A. So we're going to factor out a 9A, leaving us with 4x squared minus 9y squared. And then, of course, before we stop and say, hey, we're done, we look to see if it fits that category of continuing to factor. The difference of perfect squares? Yep. So we would say it's 9A times 2x minus 3y and 2x plus 3y. And this will be the sum of your assignment for today. But before we do that, I do want to talk about this situation because I know from my years of teaching that we're going to get a problem when you see this. Okay? When you are asked to factor the sum of squares, x squared plus 4. I don't know how many times I'll get the answer x plus 2 times x plus 2, which is x plus 2 quantity squared, or I'll get the answer x minus 2 and x minus 2, or x minus 2 quantity squared, which are both really, really not true. Isn't this a perfect square? But won't it get a middle term? 2x plus 2x is 4x, but this doesn't have a 4x in it. Or if I go this way, negative 2x, negative 4x, well, this doesn't have a negative 4 in it. So you will be tested on understanding that. You cannot factor the sum of perfect squares. Typically, they will be prime. If we were to try to graph them, they would be imaginary. We wouldn't be able to graph them. Now, there is an exception, so let's put an exception. They're not always prime. For example, I could have a 9x squared plus 36, and you can't tell me that that's prime because they have a what? So 9x squared plus 4, we can't continue to factor because we can't factor the sum of squares, but we can factor out a GCF. So just be aware of that. Okay, so that is it for today. What I would like you to do, of course, is to, in your notes, I would like you to answer this question here. I would also like you to answer this question up here. Describe a perfect square trinomial. And, of course, write a reflection. And then your assignment, 30 problems. Took me 3 minutes. It should take you 10. And we have 10 minutes left to class. Woohoo, you could leave without homework. So off you go. If you need any help, call me up.